Okay, welcome to experiment number 9. Since I've already gone through the design of this circuit in lecture, today's video is only going to be the lab procedure. So what I'd like to do is I'd like to build the circuit, the first stage alone, get it working, and then we'll go ahead and attach the second stage and get it working through that as well. So for starters, for the equipment, we have an Agilent E3620A dual DC power supply, number 688. We have a Keithley 383, number 383 multimeter, model 2000. We have a Keysight 33500 Series B waveform generator, number 793. And we have a Tektronix MSO 2012 mixed signal oscilloscope, number, don't tell me, 693. 635, same as last week. And then for doing some testing, we may be using this Fluke just to measure DC parameters. And this is a Fluke model 189 multimeter, number 458. So this is what we got, and then we're going to go ahead and just start building the circuit. So coming from our signal generator, we're just going to work left to right here. Coming from our signal generator, we're going to come into the board, and the ground lead is going to just connect directly to the ground post over here. And then the positive lead is going to go to a jumper. Let's just install a jumper over here somewhere off to the side. And that will lead into our circuit. So from the jumper then, we're going to go through our 1K RS resistor. That's a brown, black, red, which I happen to have right here. And once again, I'm going to really do my best to make the circuit on the board look just like the circuit on paper so that it's easier to know where everything is. So here's a 1K resistor, and then we're going through our first AC coupling capacitor. We're using 10 microfarad capacitors for this one. Note there's a polarity, there's a negative stripe on that side, and the negative stripe goes toward VS. So we're going to go in the negative and out the positive on that capacitor. Okay, that goes in there. And then from there, we're going to have our two resistors, R11, which we calculated to be 191K, and we're using a 200K resistor, red, black, yellow. We're going to use that as a pull-up. So that is going to go from the capacitor right side to the positive rail. Now on the pull-down resistor, what we noticed last week is that it's very, very sensitive. So what I'm going to do is R21 is supposed to be a 50K resistor, but I'm going to install a 100K potentiometer. 50K should be right in the middle of its range. And that way we can fine tune it to get our DC Q point exactly right. Remember, the beta of our transistor may not be exactly what we expected. Our resistor values might not be exact either. So this way we can actually tune the circuit to get the desired 3.7 volts that we would like on the collector of the first transistor. So that is this potentiometer here. I'm going to plug in the yellow lead to that junction, and then the other two leads, I'm just going to tie them both to ground just to keep the other one from just jumping out of the way. And we're going to set this for about 50K, which will give us our DC Q point. And that takes us into our first transistor. The transistor goes EBC, emitter-based collector, when you're looking at the flat. So let us put the transistor over here, right there. And then we're just going to put in a short jumper from there over to the middle terminal. So we have a nice short jumper over here. So that goes to the center terminal, the base, and then the emitter goes, let's see if I can bend this to a more user-friendly shape. I'm bending it to more of a U shape so that it'll fit into the spacing of the board a little bit better, like so. Get in there, U, okay. So that's our first transistor right here. The emitter is going to go through RE1 to ground. Now, if you recall, we were going to be splitting RE1 for partial bypassing, so we're going to have an 18 ohm resistor for the unbypassed part. That is this one here, brown, gray, black, is going to go from the emitter down to about there. And then we're going to have, for the remainder, a 470 ohm resistor, yellow, purple, brown, going to ground. So we're going to plug that in from there to ground. And then for bypassing, we're going to put a capacitor across the 470 ohm resistor. So that is another one of our 10 microfarad capacitors. It's just across the 470. So what we have here is the upper resistor, the 18, is unbypassed, and we calculated that to meet our gain and input impedance spec. The bottom resistor here is completely bypassed by this capacitor here. And all that's left is to install RC, which is a 3K resistor. 3K is orange, black, red. This resistor here, we got a brand new one, and we're going to connect that from the collector up to the positive rail, up to the positive supply. And that should be stage 1 of the circuitry. So this is a good time to just stop and just measure this circuit, get the biasing set correctly, and then we'll go ahead and add on stage 2 after that. So let's turn on the equipment, let it warm up. I don't think we're going to need the Keithley for this because we have a built-in current measurement here. Now we had designed this for a VCC of 10 volts. So V1 we're going to set for 10 volts. Okay, and then we just have a short lead for ground and ground. And we have our signal generator coming in, and let us connect up our scope. So we're going to have channel 1 go on the input and channel 2 go on the output. So channel 1, the yellow probe. And we're going to connect that to the right side of RS. So the right side of RS will be centered at ground. And this ground clip here, we're going to connect for channel 2. So we don't have to connect that one up because it's a long reach from there over to the ground terminal. And channel 2, we're going to put on the collector of the first transistor. It's on the bottom of the 3K resistor right there. And this one, you'll notice, is nicely within reach of the ground terminal. So we're just going to clip that onto ground over here. And that will serve as the ground for both channels of the scope. And so all that's left now is to do is connect the power. So we'll take a red wire, and we're going to go from the plus of the board over to the plus of the power supply. And we did get some movement over here, so let us now turn on our output. Let's try this one more time. The ground lead just kind of popped off, but it doesn't know that it has no choice. Okay, and then output on. Okay, looks like the scope has the averaging turned on, so let us turn that off. Trigger menu. Nope, we want acquire menu. Average off. We really don't need the averaging at this point because the signals are so small. Let's go to set the trigger on channel 2 and level. Get this thing to stand still. And it looks like we have a pretty good amount of gain right now. It also looks, let me slide these waveforms down so you can get a better view of them. So channel 2 is at the bottom of the screen, and you'll notice that channel 2 has soft clipping on the top, which means we're overdriving it. We're putting in too strong a signal in. So let's reduce our amplitude of our input because we'd like to have a nice undistorted wave. Yes, and the DC offset is supposed to be there because we're supposed to have 3 volts of DC on this collector right here. So let's do that first. Let's shut off the output and just make sure that our DC cue point is what we expected. So we have our voltmeter because we have to set it, but we do have signs of life, which is a good thing. So let us connect. Okay. Our voltmeter to ground, and then for the probe, let's use a real probe for the positive side. And we're going to set this potentiometer to get about a little over 3 volts on the collector. So volts over here. We're setting this for volts DC, which is that scale over there. And let's just put this on the collector and see where we are. Right now we're at 7 volts. So let's tweak this potentiometer to bring this down to get it to 3 volts. I'm sorry, 3.7 is what we're shooting for here. So about 3.7 volts, okay? So 3.7 volts on the collector, we should be seeing about 1 volt on the emitter, which we are, and we should be seeing 1.7 volts on the base, which we are also. So it looks like our DC bias point is pretty much set. Afterward, we will take this resistor out and just this potentiometer out and measure it, and just to verify that it was at around 50K. So, okay, so 3 volts on the collector, 3.7 on the collector, looks like we're good. Okay, so now we can go back to our signals. Let's turn the output back on. And it looks like we're getting lots of amplification and too much drive. You can see we've now got hard clipping on the bottom and soft clipping on the top. So let us reduce our amplitude, parameters, amplitude. We're down to 100 millivolts. That's good, means we got lots of gain. So we've lost our triggering. Let's reset our triggering level. The blue line should be someplace inside the waveform. Okay. And it looks like we have pretty close to 180-degree phase shift. There's a little bit of phase shift in there, but it's so small that I think we can live with it for now. And you'll also notice that the input signal here is very fuzzy and jumping around. And so what I'd like to do is turn the averaging back on, and we'll just take a measure of our approximate gain. So what we have right now, we're expecting a gain of about 70 or 80 out of the first stage. Let me look at my calculations. AV for stage 1 was supposed to be 83.4. Let's see what we're getting. So we have the input, the output is 3.9, the input is 57 millivolts. So 3.9 divided by 57 millivolts. It's close to 80? Okay. So do a quick calculation. Calculator. Let's see where we are. So 3.9 divided by 57 millivolts, 0.057 equals, only 68.4. Okay. 3.9, so our gain is a little bit low, but there are ways we can tweak it, and we still should be able to meet our gain spec if we need to. Okay. So let's go ahead and now build channel 2. I'm going to just temporarily disconnect the power supply. I'm just going to unplug it. And then we'll go ahead and install channel 2. So channel 2, we're going by direct coupling. We're going to go from the collector directly over to the base of the second transistor. And let's space that out a little bit. Let's move this second stage a little bit further over to the right. And plug it in, let's say over here. Okay. Now the collector is going to wire directly to VCC. Sometimes they do install a resistor in there just for current limiting in case there's a catastrophic failure. Oops, thank you. So the collector goes directly high, and then we're going to go from the collector of the first transistor to the base of the second transistor. Yeah, we can probably just tuck that under here, let's say. All right, well, let's see if we can twist it this way. Okay, so we're going to go from the collector of the first transistor to the base of the second transistor. That's this jumper over here. We can move this probe out of the way since we're no longer probing channel 1. Okay, like that. So that goes collector to base. And now the emitter of the second transistor has a 240 ohm resistor going from emitter to ground. And the emitter also happens to be our output node. So we're going to connect our scope onto that emitter. This is AC coupled, and we're doing DC coupled. So, but the students are doing AC coupled. I couldn't do the whole lab, for them. So now here's our 240 ohm resistor on the output. And then we finally need our third capacitor that goes from the emitter over to the load resistor. Okay, so we're going from the emitter over to RL. I'm just going to move RL all the way to the end. From emitter to RL with the negative stripe facing RL. And our load resistor we calculated is it was assigned as a 390 ohm resistor. So we're going to do a 390 to ground. Like so. And now we have stage 2 complete. So the first thing we'd like to do is just to verify that we're working. So let's go ahead and reconnect the power supply over here. And let's see what we got. Okay, notice now that we have channel 2 with no offset on it. It's just strictly DC. And we do have a good signal on the output. Okay, so we'll notice there's just a hint of clipping at the bottom. I'm not sure we're going to be able to make our dynamic range spec, but we can adjust for that. So let's go ahead and double check our specs. The gain, we're expecting a gain of 35 dB. 35 dB, let's convert that. So, I have to do scientific mode for that one. 35 divided by 20 equals, and then the anti-log of that. We should be seeing a gain of 56.2. So let's see what kind of a gain we're getting. We have an output voltage here of 3.44, an input of about 55 millivolts. So 3.44 divided by 0.055 equals 62.7. So we're very, very close to our gain spec. We pretty much made it. We can tweak the gain to get a little bit more. We can raise RC from a 3K to a 3.3K, which is the next standard value, and we can easily meet the gain spec. So the next thing is let's look at our power dissipation. We have 10 volts at 13 milliamps. We have 130 milliwatts of power. We have a 150 milliwatt power spec. We've met that pretty easily as well, so that's good. Let's check our dynamic range. So we're going to gradually turn up our amplitude until we see clipping top and bottom. And we're supposed to have 5 volts of dynamic range, and it's able to get to 5 volts, although it's not symmetrical. So if we want to get this back down to 5 volts, we can do 5 volt dynamic range, but it's not symmetrical. It's not able to make the bottom of the wave. And this is something that we're going to talk about in lecture and why that is. So, but for now, we are making a 5 volt peak to peak signal, even though it's not directly symmetrical. There could be some fine tuning going on in there as well. So the next thing to do is check our input impedance and our output impedance. I'm going to turn this back down to make an undistorted wave. Okay. You'll also notice with a little bit of phase shift that our gain in actual midband is actually going to be a little bit higher. Let's go from 1 to 2 kilohertz and see if that gets rid of our phase shift. It's still a little bit there. There's still a little bit of phase shift there, but that's okay. 2 kilohertz is still plenty slow for this circuit. That's our next topic in lecture is low frequency response. Okay. So next thing is let's check our input impedance spec. What we're going to do is temporarily remove the RS, the source resistor, the 1K, and replace it with a potentiometer. So our input impedance has to be 5K or less. So we're going to temporarily pull out the 1K. I'm just going to move it over to get it out of the picture. And then we're going to install the potentiometer. We're going to center the pot first. You always center a pot before you plug it in, no matter what you're doing. And we're going to install the potentiometer across where RS was. Okay, so now we're going to zero the pot and get our signal to some maximum value. And it looks like we're still overdriving a little bit, so let us reduce our amplitude just a hair. We'd like to have the waveform undistorted. Measurements that you take on a distorted waveform won't have any meaning. Okay, so we have an output of about 3.01 volts. So now we're going to raise the potentiometer until that reads half of that, about 1.55. So we're going to raise the potentiometer until that comes down to about 1.55. We're seeing a little bit of rippling oscillation in the circuit. That could be due to the averaging, or it could be some other instability in the circuit. We're going for about 1.55. Right about there. Okay, so now we can take the potentiometer out and measure it and see if we're at above 5K. So we'll use our handy multimeter here, set it on ohms, and see what we got. Oops, is it showing up?
Yeah, good.
Okay. It was showing up before. I think I better use leads. Yeah, it's not a reliable connection. But luckily we have probes right here. And the input impedance should be 5K. Remember we did the calculation for 6K. Let's see what we're getting here. 4.93K. So we are very close to 5K. To raise the input impedance, we can just replace this 18 ohm resistor here with the next level value up. So we'll make a note to do that and see if this improves the input impedance at all. So why don't we do that? So what I'm going to do to improve our input impedance spec, we're close, but we're not quite there, is let's increase that 18 ohm resistor to a 20 ohm resistor, red, black, black. So I'm going to pull out the 18 and install the 20. And let's do our input impedance measurement again.
You said 20K or 20 ohms?
Just 20 ohms. Yes. Yep. Okay, so now let's go ahead and reinstall this potentiometer here from the input to the signal generator. And we can now set this again for 1.55. Let's shut the averaging off so the signal is a little bit more centered.
Why?
Yeah. Oh, it really doesn't like that. It's oscillating like crazy. Oh, because I'm touching it. Okay. So let's again set this for 1.55. There's something unsettling in the room that when I touch this thing, it goes into oscillation. It must be my electric personality. 1.48. It could be. It's very touchy. A little better. Not really changing much, is it? It seems to like 1.48.
Right.
Okay. Looks like I'm going the wrong way. Let's try this way. Still 1.48. Okay, that's about as close as we're going to get it, I think. So let's see what we have now, measuring with the ohm meter. 5.5K. So we've met our input impedance spec. It's got to be 5K or more. Okay, so that's good. So let us now reinstate our S. I'm just going to move it back over and connect up the left side again. We have a nice clean output. As long as I don't touch it, it's fine. So now let's check the output impedance spec. What we're going to do is going to unplug the load resistor and install this 200 ohm pot. So we're expecting about a 100 ohm input impedance. The guideline is get a pot of twice that value, so that 100 ohm will be in the middle of the range. And again, we're going to center the pot before we plug it in. We will temporarily just disconnect this 390. I'm just going to leave it here plugged into an empty spot so we don't forget where I put it. And let us connect the potentiometer. Right now we've got an output of 2.60. And so what we'd like to do is we'd like to set this pot until it drops to 1.30. So we'll connect the pot from output here down to ground. It won't plug in. It has no choice. It has to plug in. Sometimes the breadboard prongs get a little bit tired. There we go. So we'd like to set this pot until we get down to 1.30. Okay. Okay, now what's happening is we're clipping, which means that we're overloading it. So what we do to fix that is we reduce our input signal and try it again. So let's go back to our input amplitude. Right now it's 20 millivolts peak to peak. Let's see if we can get it down to, okay. And let's go back and set our unloaded output voltage here. 1.4. And now we're going to try to get the pot down to 0.7. Let's see if we can turn this up a little bit. It's still, well, we're close to 0.7. Right about there, and it's still clipping a little bit. Let's make the input, see if we can get it any smaller. We want to get the output wave undistorted. So let's try this again. Now it's undistorted, but we're down to a 5 millivolt input. That's very small. So we have now an output of about 0.7 volts, 0.688. And now let's go for half of that, which is around 0.35, and hope it doesn't clip. So right about there. So we had to reduce our input signal because our output started to clip under this heavy load. Remember, this is a 100 ohm load, and we designed the circuit for a 390 ohm load. So we are loading down the circuit to try to match its output impedance, but we're pretty much there. So let's take this pot out now and measure it and see what we get for output impedance. The spec was, I believe, 100 ohms or less, and we're at about 16 ohms. We clobbered that spec. So the output impedance of the circuit is very, very low. If we had done the lab on common collector outputs, we would see that these output impedances are very small. So, but this is our first opportunity to see that. Okay, so that, I believe that's all of the specs. We're still at 130, 140 milliwatts, 135 or so. We're under 150, which is good. And then the only thing I'd like to do is let's go back and revisit our gain spec. So we had a 3K resistor for RC, and our gain was just a little bit off. Right now, we're going to need to turn the averaging on to check our gain. Averaging on. And That's turned up as big as it's going to go. Now this is not going to be a very reliable measurement, but we have, let's see if we can turn our amplitude back up. We can keep turning this up until the output doesn't clip anymore. And we were pretty close to 180 degrees out of phase. That's a good sign. Okay, we're starting to see some clipping now, so let's back it down a little bit. Okay, undistorted waveforms, we have a gain of 3.38 divided by 55 millivolts. We're just going to verify that our gain still isn't very good. So 3.38 divided by 0.055 equals 61.4. And I think we have to get to a gain of 63 if memory serves. So let's try replacing the 3K collector resistor with a 3.3K. It's the next value up. Remember, R sub C gets you more gain. So we're going to plug that in from power to collector. Right there. And you can see we've definitely gained some gain because we're now overdriving, which we weren't before. So let's turn our input signal down a little bit to try to get it out of clipping. About there. And let's check our gain once again. So we now have 2.58 divided by 37 millivolts. So 2.58 divided by 0.038 equals, we now have a gain of 68, which does improve our spec. So 68 divided by 20 equals, and then, oh no, it's the other way around. 68 log, okay, inverse log, log base 10 times 20 equals 36.6 dB of gain, and we're spec with 35 dB. So at this point, our amplifier has met all of its specs. Okay. So what we're hoping to see is that if you need a little bit more gain, RC is a quick way to do that. We saw that we also made an adjustment for input impedance, and what we did for that is we just slightly raised the unbypassed section of RE of stage 1. And these are the kinds of lessons that you can write about in your lab report, what kind of changes we made to meet our specs. Okay, I think that's it. In fact, we're down to 11 milliamps of power, so we're actually more efficient with power than we were before. We have very much exceeded some of our specifications. Okay,